Welcome back, everybody. This week we're going to be learning about our own Milky Way galaxy, and I just wanted to talk a little bit about what I think is the most exciting thing about our Milky Way galaxy, and that is that most of it we can't even see. Because of the way we've studied the motions of the stars over the last few decades, we've learned that the motion that we see is caused by the gravitational influence of more matter than is actually shining in the light that our telescopes detect. In other words, when we look with gravity, we see more stuff than when we look with light. And that's pretty amazing. That gives rise to this idea of something called dark matter. And there's a couple videos I'm going to have you watch, one in particular about Vera Rubin and her discovery of dark matter, looking at the rotation curves of galaxies. But to get a better understanding of how she did that work, I have a couple of simulations that should allow you to explore this. So let me go ahead and start those up. They're going to be in the simulation section of your module this week. Okay, so we're going to first start by looking at galaxy rotation curves. So a galaxy rotation curve is a way of measuring the mass that's inside of a galaxy. And what we do is we measure the velocity of stars as they orbit the center of the galaxy. And we do that by looking at something called their Doppler shift, or their red shift, or their blue shift. And we've talked about this before in terms of how we find out about exoplanets, but we use the same technique to learn about the motions of the stars. So if a star is coming towards us at a high velocity, it's blue shifted. Its spectrum is blue shifted. If it's moving away from us, it's red shifted. And if we measure how that goes, we can measure the velocity of the star as it goes around the center of the galaxy. And from that, we can get what's called a rotation curve. Now, because things move by the influence of gravity, when we measure their motion, we're really measuring the influence of the forces on them, and that force is due to other mass inside the system. So a couple of models present themselves. One is we have the entire mass of the galaxy located at the center. And if that's the case, then an orbiting object would represent its motion would represent the mass of this object in the center, and we could directly measure the mass by measuring how fast it's going around, just using Newton's laws. That would give us a direct measurement of the mass in the center. We also have the mass of all the other stars we can see, right? So you've got the mass concentrated in the center, all these other stars we can see, and that influences the motion of the stars. And so we should be able to see that influence on the motion of individual stars in the galaxy. And then finally, if there's anything else out there that we can't see that is influencing these objects gravitationally, that will affect their motion as well. So what you're looking at here is the way that we model the distribution of material in our galaxy. This is a graph of the velocity of the stars as we move away from the center of the galaxy. So imagine we're looking at our Milky Way and we're measuring from the center, we're measuring the velocity of the stars as we go away from the center. What do we expect, and what do we actually measure? So if I just had mass concentrated at the center of the galaxy, if there was nothing else but just this very, very, very dense central mass in the center of the galaxy, I can simulate that by just dragging up this point mass slider. And when I do that, I get a curve that looks like this. This is basically Kepler's law. It says the closer you get to the star, or to the central mass, the faster you're going. The more mass you have, the faster you're going, and it drops off as you move away. Okay, so that's our central mass. That clearly does not at all represent what we're seeing in our galaxy. And that makes sense, because when we look at our galaxy, we see all these other stars. So let's go ahead and start to drag up the stellar mass and see how that influences the rotation curve. If I go ahead and do that, I see now that because there's distribution of material that's not concentrated in the center, that actually ends up speeding up the stars a little bit as you go further away. And I can start to play around with this and try to match the curve. So I'm going to drop this point mass down so I get something that matches the data. And it turns out there's really not that much mass. It's located in the center. I can put a little bit in, but it actually matches the data more to put almost none. Right? It tells us that most of the mass of the galaxy is distributed throughout it. Then I start to drag up the stellar mass to try and match this blue curve to these red lines, right? And this is what Vera Rubin was doing, right? She was measuring the velocities of stars as they changed, moving away from the center of the galaxy, and then she was matching that with known laws of physics. So this is basically representing all of the mass that we can see, so all the stars in our galaxy. And the one thing you'll notice is that the velocity we would expect based on the stars we can see is not the same as the velocity we measure. And so something has to account for this discrepancy. And the solution to this discrepancy is that there must be some kind of material out there that's massive, that interacts gravitationally with everything else, but we can't see it. In other words, it doesn't interact very well with light. But let's just pretend that there's this stuff called dark matter, which is stuff that influences things gravitationally, but you can't see with your eyes with light. And we'll go ahead and see if we can ramp that up. So if we ramp up the dark matter, we can start to bring up that velocity curve until it matches. Okay, and then you can kind of play around with this, trying to see if you can match it really well. We're going to have another simulation to try this a little bit better, but you can match it pretty well with those things. And what I want you to notice here is that when we have a model that reaches pretty good agreement with the observations, what we find out is there's 10 to 100 times as much dark matter in our galaxy as the matter that's shining with light. That's remarkable, right? This should kind of blow your mind that we're seeing, in quote, with gravity, 10 to 100 times more material than we can see with our eyes. It's actually even a bigger statement than that, because it's not only we can't see it with our eyes, we can't see it in X-rays, we can't see it in ultraviolet, we can't see it in infrared, we can't see it in radio waves. It doesn't interact with light at all. So this is a new kind of matter. It's a type of matter that doesn't interact with light, but does interact gravitationally, and it's something we call dark matter. And this dark matter, I'll be perfectly honest with you, we don't have really a very good idea of what it is. We just know that it exists. And we know that because we see it with gravity. We just don't see it with light. And while that's odd, it's not that odd. I mean, if you think about it, right? We actually know of particles that don't interact well with matter and light, and that those are neutrinos, and those have been detected. So this is just another type of material that doesn't interact with light or matter. Now, when I say light or matter, it means it doesn't block light. It doesn't emit light, it doesn't reflect light, it doesn't scatter light. It's just completely invisible to the electromagnetic spectrum, but not to gravity. Okay, so this is this stuff called dark matter, and this was a big deal, right? But what it also does is it brings out this whole new way of seeing things, right? We can measure the gravitational influence, and even if we can't see what these things are, we can detect them. And this has kind of developed a whole host of a branch of astronomy of people seeing stuff with gravity. So the other simulation I have to show you, if we go back to our simulations section of our module with galaxies, is this thing called the dark matter simulator. And this is a little bit more sophisticated model in that what it's showing us is a representation of the density of dark matter as a function of distance from the central mass of the Milky Way. So what you're seeing on the right-hand side here is the motion of the stars, and right now there's no mass, so there's no motion. And what I'm going to do over here is I'm going to start lifting up a number of the mass of dark matter as a function of distance. So we're going to try to map out what the distribution of dark matter is. And then this is a similar rotation curve for the Milky Way that we just saw before. And when these red dots match that blue line, we will have a good model of what the distribution of dark matter looks like as a function of distance from the galaxy. So you can just start raising these up, and you find that, if you put this one at about 74, and then I put this one up right around 7. And again, I'm trying to match these red dots to this blue line. You can kind of play around with that. Put that one there, put that one there. And now you'll notice on the right-hand side, as I'm doing this, the stars are moving, changing their velocities, because the velocity distribution curve is changing as I change the mass. But you can see, because of these wiggles, we can start to get a shape to the dark matter distribution of our galaxy. And that is what the dark matter distribution of the Milky Way looks like, right? So this is a kind of a game that astronomers can play, is we can take the laws of physics, the understanding of gravity, we can use that to predict the motion, and then we go out into the galaxy and measure its motion and determine how much stuff is there independent of the light that it emits, reflects, or blocks, which is pretty amazing. And it turns out there's lots more evidence for dark matter. We're going to talk a little bit more about that later. You're going to read about that in your textbook. Lots and lots of evidence for dark matter in our galaxy and in the universe beyond our galaxy. And it turns out that there's about 100 times more stuff in the universe than you can see with the electromagnetic spectrum. Pretty amazing. Totally flabbergasting and totally exciting. All right, so that's what you're going to be learning about this week, and we will talk to you later.